Hey there. In this lab, we're going to be looking for something called the coefficient of kinetic friction, which is represented by the symbol μk. Mu is the Greek lowercase letter for m, and the subscript k indicates that the coefficient applies to the kinetic frictional force rather than the static frictional force. The coefficient of friction, whether it's a static or kinetic friction, depends only on the types of materials that are sliding against one another. In this case, we'll be looking at a wooden block sliding across the surface of the lab table. Since our object will be in motion, this will be an example of kinetic friction. You can think of the coefficient of kinetic friction as the stickiness factor between the two materials. The coefficient ranges anywhere from between 0 and 1. Closer to 1 means greater stickiness factor and stronger frictional force. Value closer to 0 means lower stickiness factor and a weaker frictional force between the two objects. As an example, you'd want something like the asphalt or concrete of the road and the rubber between a car's tire to have preferably a higher coefficient of friction, because that gives you more maneuverability and control if you have more friction between the tire and the ground. We will use our equation that relates kinetic frictional force to the normal force. That's Fk, kinetic frictional force, equals μk, the coefficient of kinetic friction, times Fn, the normal force, in order to determine the coefficient of kinetic friction for our two materials, wooden block and lab table. Let's take a look at our setup. Right here you can see we have our wooden block. Dimensions unknown, but it doesn't really matter. We're going to keep it flat as you see it here instead of having it sideways like this, so that we can put stuff on top of it. We're actually going to put more and more mass on top of our wooden block here, and that should effectively change the normal force. So we'll be able to have multiple data points. We got this special thing over here, which is a dual range force sensor. You can plug it into this nifty little tablet, which we're going to do, and you'll see represented on my other screen. We'll plug it into that with this little plug there, and then I can pull from the hook. I can pull on something, and it'll tell me with how much force I am pulling on that thing. So we have a wood block here that we're able to pull across the surface of the table. Now, this might seem ridiculous, but I've got a long string here with a paper clip at both ends. You've seen it before. And we're going to attach a paper clip to one end of our block and leave it over here. And then I'm going to use that force sensor and my tablet, and I'm going to connect that over here. The reason I'm going to do that is because, as you can see from the dimensions of the block and the dimensions of my force sensor, the force sensor is significantly thicker than our block. And if I were pulling it, I don't want to pull the sensor directly across the table, because then there's friction between the sensor and the table, and that messes up the stuff I'm figuring out about my block and its coefficient of friction between the table. So I'd have to hold my sensor up high, but then I'd be pulling at an angle. So to avoid that, I've created a long string so that I'll be able to hook onto the string. Oh, there it goes. Man, I don't have time for this. So I have my string going down the length of the table, so I'll be able to easily pull directly horizontally on our block without worrying about pulling at an angle or having any friction between my sensor and the table. What else? We have some masses that we're going to use to increase the normal force for each trial, and I'll put those masses on top of my block each time. We'll use, I don't know, these guys. Each of these are about 200 or something. I got a 500 and another 200. I think that's what I use. All right, so there's all the stuff we're using. We got our extra masses here. These small ones are each 200 grams. I've got my, this is a 500 gram mass. I'll tell you what we're putting on each trial. We've got our wooden block, we've got our paper clips and string, we've got our sensor, we've got our special nifty tablet that can read the force values. Now, a really important part of what we're about to do, when we want to find out the coefficient of kinetic friction, and we're going to use this equation Fk equals mu k times the normal force. Remember, mu k, that's the coefficient of kinetic friction. When we do that, we're going to know the normal force, which will be the force of the table pushing up on my block, and we're going to be able to know the Fk, the kinetic frictional force. In order to figure out what the kinetic frictional force is, though, we have to do something, and so we're going to pull the block, or I'm going to pull the block. And so this force sensor is going to measure how hard I'm pulling that string, which will be equivalent in this case to the amount of friction that is acting on the block. And the reason it's going to be the same amount is because I'm going to pull the block at a constant speed. If I pull the block at a constant speed, that means its acceleration is 0, and all the forces acting on it must balance out. The force of my pulling must be balanced out with the kinetic friction that is pointing in the opposite direction. If I pull it too hard and it speeds up, then my pulling force on here is not going to be the same as the kinetic friction because they're not balanced. If I pull with not enough force, then I'm not even going to be able to get it moving. And you'll see in our graphs that we are going to look at for each of our trials that there's going to be a big peak where the maximum static friction happens, and then there's going to be a drop-off and then kind of a squiggly, more or less constant value in our graphs for each trial. And that more or less constant value there, that's representing the kinetic frictional force. All right, so to get started with our first trial, I need to measure, first we're just going to have I'm going to pull just the block, and you'll see on the screen the mass reading from the triple beam balance of how much mass this block is. I have no idea what it is. So we're just going to put that on the screen as me measuring it, and then you can read off the value from that. I'm going to attach this paper clip right here. Okay, and then we're going to go and pull this guy to constant speed. I got to attach this dude here. Okay, so here we go, pulling just the block. I'm going to pull it, do my best to pull it at a constant speed, and we'll see on the graph the big peak, that's the maximum force I had to pull to break the static friction and get it moving. And then you'll be able to see that lower, more or less constant value of the kinetic frictional force. All right, now I've just put, I still have my block, but now I've added this single mass on top of it. There you go, you can see how much that is. Okay, it should be 200 grams plus the mass of my block. And here we go. We'll give it a pull at a constant speed. There it is. Here's 200 grams plus the mass of the block. Constant speed, horizontal. Okay, we can see our maximum kinetic friction up there, a maximum static friction. So we can see our maximum static friction up there gets broken, and then here's a portion of the graph we can look at. That's the force balancing with the kinetic friction. So we're going to just analyze that force and get the mean or average value. If we just kind of balance out a little bit of noise in there for the kinetic friction, there's our mean value, 0.579 newtons. That's the force I pulled on the block with when the block had 200 grams of mass on top of it. We also need to add in the mass of the block itself. And so this pulling force of 0.579 newtons is being balanced with the kinetic frictional force. Since I'm pulling at a constant speed, they must be balanced, no acceleration, so the forces must balance. So 0.579 newtons is equivalent to our kinetic frictional force for this first trial with 200 grams on top of the block. And again, we should see a spike for when the kinetic or static friction rather is breaking, which should be a higher force amount, and then the lower value that's constant for the kinetic friction. Here now I have 2 of the 200 gram masses on there, plus the weight of the block. Let's take a look. Constant speed. Here we go. Again, we should see the big spike for static friction being broken, and then the lower, more or less constant value for the frictional force. Okay. You can see our maximum static friction. I keep saying kinetic. Maximum static friction is higher now. We had more mass on there, so we have more blocks more squished against the table. Our normal force has increased because we put more mass on top of it. Let's take a look at our static friction, our kinetic friction. My goodness. Now we'll take a look at our kinetic friction. It should be balancing with my pulling force. That's what this force is measuring, the pulling force. It should be balanced because I did it at a constant speed. Let's see what the average or mean value is. 1.006 newtons. Now that's where we're going to be looking for the next few trials. What is the mean or average value of this squiggly blue line here, which is representing the pulling force, which is constant as I drag it at a constant speed. And because it's constant speed, it's balancing out with the kinetic frictional force. So we can say that the average of this squiggly blue force over time function, this average value, just draw a flat line across it, right about there, that value 1.006 is equivalent to the kinetic frictional force. Now we've got 3, all of them 200 grams, plus we have the mass of our block, whatever you read that off as. And we're going to give it a pull. Here we go. Okay, that's 600 grams on top of our block. So total mass is 600 grams plus the mass of our block. Like a sled for the weight. And then we've got another 200 gram mass I'm going to put on there. So now we have 4 200 gram masses sitting on top of our block. Don't remember to include the mass of the wooden block itself. And nice and horizontal, constant speed pull. Here we go. All right, here's 800 grams plus the mass of our block. All right, now I'm going to add on the last mass, which I don't even know if you can see in the camera. There you go. 1/2 kilogram, 500 grams. So I'm adding that on top. So now our full mass will be the mass of the block plus all of those guys we had previously. So 800 grams plus now another 500 grams. Plus, don't forget the mass of the block itself. Okay, we're going to pull nice and horizontal. Constant speed. I was going to break the string for a second. Okay. All right, so that was 1,300 grams plus the mass of the block. Okay, so here we go, pulling just the block. I'm going to pull it, do my best to pull at a constant speed, and we'll see on the graph the big peak. That's the maximum force I had to pull to break the static friction and get it moving. And then you'll be able to see that lower, more or less constant value of the kinetic frictional force. After collecting your data, you should have information about the pulling force that I was pulling with to keep the block moving at a constant speed. Because it was moving at a constant speed, that means my pulling force was balancing with the kinetic frictional force. So whatever value you saw on that graph as the average value of, we see it go up and spike and then come back down, and then it's kind of squiggly. All right, so the average or mean value of that lower flat squiggly line, which represents the kinetic frictional force. Whatever that value is, the average value, that's the value you can use for the frictional force, and that should correspond to each trial that we did. The first trial was just with the plain block by itself, and then we added subsequently more mass on top for each subsequent trial. That means every time we added more mass, the normal force was increasing. And as we can see in that equation, Fk equals mu k times the normal force. If we make the normal force larger, then the frictional force is going to grow proportionately. And we should see that in the data from the force sensor on the graphs. So the challenge now, and there are a number of ways you could do it, but it's to figure out what mu k, or the coefficient of kinetic friction, is between block and lab table, regardless of the amount of stuff we stack on top, the coefficient should stay the same because it should only depend on the type of material. So this is wood, and then the surface of the lab table is wood, but it's coated with something, so it seems a little slipperier than normal wood, actually. But you're probably going to get somewhere around 0.2 to 0.25 is the normal coefficient of kinetic friction for wood sliding against something similar to wood. The main challenge here is you do need to provide a graph. I recommend you use QuickGraph 5.0, but you want to use a different website or something, that's fine. But in your graph, I would like to see you create a graph such that the slope of your graph is equal to the coefficient of kinetic friction. Which means, I'll give you a hint, you're going to use that equation, Fk equals mu k times the normal force, but you just got to figure out what you should put on the y-axis and what you should put on the x-axis such that the slope is equivalent to mu k. And so if you fit a trend line, hopefully it's linear, then that trend line, well, it's going to have a slope, and it'll tell you what the slope of your graph is. If you set up the graph properly such that the slope is equivalent to mu k, then knowing that slope from the trend line will be your answer. And that'll be a good way to get a good average value based on your 6 different trials. Good luck.